Happy to open the last session of today with a review talk by Shota Komatsu. He will tell us about integrability in ADS-CFT. Please.
Okay, thanks a lot, and let me thank the organizers for putting together this great event. And today I'm going to talk about ADS-CFT, an application of integrability to gauge theory, which happens to be a subject Feynman also wanted to understand from this picture. So this is the last blackboard of Feynman, and he had an idea of describing like a soft physics of QCD happening in two-dimensional transverse plane using integrability. And if you want to know more about it, I would recommend reading this paper. And also there are nice slides of colloquium by Hiroshi. Okay, so let me start with this disclaimer. So today, although integrability can be applied to several theories, so today I'm going to focus on n=4 supermels in 4 dimensions. However, let me just mention that recently there was a very interesting paper by these authors in which they found some new structure in n=2 superconformal field theory. And the goal of the talk today is to give you a feeling of what the quantum spectral curve is and explain some application, and also to explain some recent developments involving DeBrains, in particular determinant operators. So there are things that I'm not going to discuss, for example, hexagon or Yangian from defects. And if you're interested in those topics, please see these references. But let me just highlight, there will be talks today and tomorrow on related topics. So let me start with this question. So what do we mean by n=4 supermels is integrable? To answer this question, so let's consider the correlation function of single trace non-BPS operators. So if you expand it in the large n limit, you get this power series of 1/n squared. And on top of that, there will be correction coming from d instanton or instantons in Yang-Mills theory. And furthermore, we expect that there will be correction of the form e⁻n squared, which come from black holes or single boundary wormholes. And there might also be correction which is doubly non-perturbative. And our expectation is that we can compute terms on the first line, but not the terms on the second line. And by now, we also know that some correlation functions involving operators whose dimensions scale like n are computable, which are like a duo to DeBrains. However, at the moment, we don't have strong evidence to believe that operators whose dimensions scale like n squared are computable. And a short summary is that as long as operators do not back react ADS5 times S5 geometry, there is a chance that we can compute things using integrability. So next, let me address this question. Why should we care? Why should we care about solving n=4 supermels? So the first reason is that it will give the first example of solvable interacting gauge theories in 4 dimensions, which is a great achievement if we succeed. But to me, what's more important is that it gives us a data point about string theory on Ramon flux background. And at a more technical level, there are qualitative and quantitative similarities with pure Yang-Mills theory, for example, BFK physics. And in addition, if we succeeded in solving planar n=4 supermels, then we can use it as a starting point for conformal perturbation theory or Hamiltonian truncation. And more speculatively, it might tell us how the worldsheet emerges from the gauge theory, which I view as a simpler version of the question, how do bulk and gravity emerge from quantum mechanics? So let me just give you one example. So an example is a fluctuation on GKP string, a so-called GKP string, which is dual to null Wilson lines. And as you can see in this picture, at strong coupling, namely on the ADS side, the string can vibrate along the radial direction. However, at weak coupling, if you do the computation, then you see no mode corresponding to the radial fluctuation. So this problem was addressed in these papers using integrability, and they found that this radial mode is nothing but the 2 fermion bound state, which becomes marginally stable at strong coupling. And I should also mention that a similar mechanism for probe brains was discussed in a series of nice papers here. And finally, once we succeed in solving n=4 supermels, hopefully it might give us some hints about the worldsheet dual of pure Yang-Mills. And I guess there will be some related comments in the talk by Matthias tomorrow. So before explaining how integrability works, let me just give you the status of the research or status of the field. So integrability was first discovered at weak coupling in the analysis of the two-point function or the spectrum of local operators. And then later it was generalized to finite coupling, but in the limit where the length of the operator is very large. And finally, in 2009, people succeeded in computing the spectrum at finite coupling and finite lengths using a method called thermodynamic betanzhe. And then the method was reformulated into a beautiful and elegant formalism called quantum spectral curve in 2013. And similar development happened for three-point function. First, people analyzed it at weak coupling using the spin chain method. And then later, we succeeded in generalizing these results to finite coupling, but in the limit of large lengths. And that is the method called hexagon. And for a while, people tried to generalize this to get the finite size three-point function, but so far we didn't succeed. However, 2 years ago, we realized that if you consider a slightly different set of operators, which are determinant operators, then you can actually generalize the thermodynamic betanzhe and directly compute a finite coupling and finite size three-point function. And also recently, there were many attempts to try to know something about three-point function using quantum spectral curve. And I'm going to talk about these new developments. But of course, I'm going to review the basic stuff as well. So, and my main message, the main message of today's talk is n equals 4 super mils is half spin chain and half large N gauge theory or matrix model. Well, of course, this might sound like a trivial statement to some of you, but I'm going to convince you that there is some deeper meaning. Okay, so let's start with the basics. So in 2002, Minahan and Zarembo found a relation between a one-loop dilatation operator and a Hamiltonian of the spin chain. And their idea is to consider this kind of single trace operator made out of two complex scalars, y and z, and map y to downspin and z to upspin. And under this mapping, they found that the one-loop dilatation operator can be mapped to a Hamiltonian of so-called Heisenberg spin chain, which is given by this. And what is nice about this Hamiltonian is that this Hamiltonian turned out to be solvable by a method called betanzhe. So what is betanzhe? So the betanzhe is a simple two-step procedure for constructing the eigenstates of this Hamiltonian. Step one, you write an ansatz by viewing upspin as the vacuum and downspin as an excitation. And the ansatz for the wave function is very simple. It's just a sum over plane waves. And the only unknown input for the ansatz is this S matrix, or this S factor, which you multiply whenever you swap the order of momenta. And step two, we just impose that it is an eigenstate of the Hamiltonian. And as soon as you impose it, then you immediately discover that this S is fixed to be this form. And this U is related to momentum of particle in this way, and it's called rapidity variable. And on top of that, you find that these momenta need to satisfy algebraic equation, which is called Bethe equation. And if you want to compute the energy, what you just need to do is to solve this Bethe equation and determine all P's and Q's, and then use this formula to compute the energy. So this was the story for the one-loop dilatation operator. So what should we do if we want to know the finite coupling spectrum? So for the finite coupling, we first need to assume that integrability persists at finite coupling. And once we assume it, then a general theory of integrability tells us that we can still write the Bethe equation at finite coupling as long as the length of the operator is sufficiently large. So this is the equation. So however, to really use this equation, we really need to determine this S of lambda, in particular, the dependence on lambda. So this problem was solved essentially by Weisert, and who realized that actually this S of lambda can be determined by imposing the so-called centrally extended SU2/2 square symmetry, where SU2/2 square part is just a subgroup of superconformal symmetry. So this is surprising. because in ordinary quantum field theory, just imposing the symmetry is not enough to determine the coupling constant dependence. And the magic here comes from the central extension P and K. So let me just tell you what they are. So on the gauge theory side, it's actually very easy to understand what these P and Ks are. In order to do that, we just need to remind ourselves the basics of supersymmetry. Supersymmetry acting on boson gives you fermion. And if you take another supersymmetry generated and act it on the fermion, then you get several terms, but in particular, you get this term, which is given by the commutator between a complex scalar field and a boson. And this is precisely our P. And what is most important here is that this P comes with GM Mills, and that's basically the reason why P knows about the coupling constant dependence. And this relation can be summarized into this anticommutator, Q and Q prime anticommutes to P. And interestingly, these P and K also have an interesting interpretation on the spin chain picture. And in order to see that, we just need to take this definition of P and then act it on a spin chain state, which consists of a bunch of Z and one Y. And because it's commutator, if it acts on Z, you just get 0. So non-trivial term only comes from the action of P on Y, and which is given by this. And as you can see, so this is nothing but a discrete translation. So this nicely embodies the fact or principle that I wanted to advocate, that n equals 4 superMOS integrability is half spin chain and half gauge theory. And once you determine this S of lambda, and using the beta equation, we can actually determine all perturbative 1 over L correction at finite coupling, at finite root coupling. However, if you're really interested in the finite size spectrum, you also need to know the exponential corrections. But the exponential correction can be computed by a method called thermodynamic betanzhe, which I will describe later. And using that method, people basically created this kind of plot, which nicely interpolates weak coupling answer and the strong coupling answer. However, one problem about this TBA approach is that it works for some operators like Konishi state, but generally it's actually hard for most operators because TBA equation is an infinitely many coupled integral equation. So we need a better method. That is quantum spectral curve. So to tell you what the quantum spectral curve is, let me just go back to the simplest spin chain, which is the Heisenberg spin chain that I was talking about. And so for the Heisenberg spin chain, the beta equation, if you write it explicitly, you get this expression. And now I want to reformulate this beta equation. In order to do that, I introduce what's called Q function, where this is just like a polynomial whose roots are given by this uj. And you can actually show that this beta equation is equivalent to this functional equation. And in order to see that, you just need to set this u to be uj. Then the left-hand side becomes 0 because of this q term, whereas the right-hand side gives you this kind of a bit complicated expression. But if you massage this expression, you can easily see that they are the same. And although not obvious, this equation, this functional equation, can be further reformulated into this equation if we introduce another variable q twiddle, which is defined by t in this way. So this is the central equation in the quantum spectral curve approach, and which is called QQ relation. And mathematically, you can think of it as a kind of generalization of the Plucker identity of Grassmannian. So what's nice about this QQ relation is that actually you can generalize it to the full n equals 4 superMOS, although the form is a bit more complicated. However, there was one problem about QQ relation. Actually, QQ relation does not depend on two-foot coupling. And in fact, the same relations hold both at finite coupling and also for spin chain at weak coupling. So in that sense, this QQ relation is intrinsically a spin chain relation. And in order to incorporate this coupling constant dependence, we need to use the other side of the coin, which is the fact that it is a Largian gauge theory or matrix model. So let me explain what is the other half of the coin in the simplest possible example, which is the Largian Gaussian matrix model. So of course, in the Largian Gaussian matrix model, there is no dilatation operator to diagonalize. But there's something that you can still diagonalize, which is actually two-point function of single trace operator, because the two-point function of this kind of single trace operators in the large n limit are non-diagonal. So you can try to diagonalize it by constructing some nice linear combination of single trace operator. So this problem was addressed in this paper, and they found that actually if you replace this single trace operator with a linear combination of single trace operator, which is given by Chebyshev polynomial, then you can diagonalize the two-point function. And a nice feature about this Chebyshev polynomial is that if you write it in terms of what's called Zhukovsky variable, it takes exceedingly simple form, which is given by this. And this is basically Q function or quantum spectral curve for a Gaussian matrix model. So there are several nice features of this Q function for the Gaussian matrix model. First, it is most naturally defined on the x-plane, which is a double cover of U. So if you solve this equation, you get this expression. And by the way, this square root is nothing but the Wigner's semicircle, and which happens to be also the inverse of the resolvent. Second, the charges of the operator can be read off from the asymptotics after you go into infinity, like this. In other words, you can interpret this Q function as a degree L branch covering of CP1. Third, and most importantly, it satisfies what's called gluing condition. So if you take this Q function and then analytically continue through this branch cut, then x goes to 1 over x. However, because of this form, you can easily see that this Q function is invariant under this analytic continuation. This is the gluing condition for this Q function. And this third feature, the gluing condition, you can actually naturally generalize to n equals 4 supermills. And because in n equals 4 supermills, we have several matrices, so we have several Q functions. So the gluing condition gets a little bit more complicated, but you can still write it. And what is most important here is that together with the QQ relation that I talked about earlier, these two relations completely determine the Q function. So this is another manifestation of the principle that I was advocating. And similarly as the Gaussian matrix model, if you want to read off the charge, then you can read it off from the asymptotics at infinity after solving these two equations. And by using this quantum spectral curve, people succeeded in doing many computation, but and also in particular, people succeeded in computing analytic expression for 11 loop anomalous dimension of Konishi operator. It's a bit long, but it's nice because it's very explicit. So another nice feature so in the case of Gaussian matrix model, the correlation functions are also given by integrals of Q function. For example, so this you can show by simple a matrix model using simple matrix model techniques. For example, two-point function is given by integral with this measure, whereas the three-point function is given by the integral with this measure. And I should emphasize that this is not just a made up, because actually they describe a topological subsector of n equals 4 supermills. So given this, it's kind of natural to hope that maybe something similar is also true for n equals 4 supermills. So for example, maybe we can write some expression like this. Unfortunately, we haven't yet achieved this, but in the past few years, there have been a great progress for constructing the measure for the two-point function at weak coupling. And the basic strategy is to impose this kind of a slightly generalized orthogonality condition. And by doing that, they succeeded in deriving d mu2 for GL and M spin chain, non-compact spin chain, and also spin chain with general representations. So here, I just wanted to show you the simplest possible case, which is the SL2 spin chain of length L. And that is given by this integral. Actually, the two-point function is already given by multiple integral, and the number of integration variables is given by L-1. And here it's a bit interesting because instead of usual Van-der-Monte, you have some a weird Van-der-Monte, like a half Chern-Simon matrix model, half usual matrix model. And given this structure, I think it's kind of interesting to ask whether we can derive it or generalize it using beta gauge correspondence. So this expression is only for weak coupling, namely one loop. So obvious next steps are to generalize it to finite coupling and also to figure out the measure for the 3-point functions. So there are several difficulties that we expect. For example, the number of integration variables is actually going to increase as you increase the loop order. The second difficulty is that measure for the 3-point function is going to be different for the measure for the 2-point function because of the double trace operators. So I don't have time to explain that, but this is a kind of like a natural expectation. Nevertheless, we should be optimistic because in some cases, actually you can compute this measure for the 3-point function, for example, in some fishnet limits or from localization. Okay, so this was it for the quantum spectral curve. And now I'm going to move to the second topic, which is about DeBrains and determinants and G functions. So in 2 years ago, we found a new class of solvable correlation functions, which is basically the 3-point function of 2 determinant operators and 1 single trace non-BPS operator. So there are several nice properties of this 3-point function. For example, it is in some sense analog of baryon-baryon meson vertex in large NQCD. So this is like a joint version of that. And secondly, this has a nice holographic description. This determinant operator is dual to DeBrain in ADS, which is called giant graviton. And also another nice feature is that you can compute it at weak coupling using matrix product state and at finite coupling using the techniques of Warchi G function, both of which I'm going to describe in next slides. But before moving on, I just wanted to mention an analogy with FZZ T-brain in a minimal string, which corresponds to insertion of determinant of E minus H in the matrix integral, where H is the matrix here. So in the case of FZZ T-brain, so this parameter E basically controls the position at which FZZ T-brain ends. And similarly, if I introduce a generalization of this determinant operator by introducing parameter X, then this X basically controls the position of D3 brain in ADS5 times S5, in particular inside S5, in particular inside S5. And as if you increase X, then like a D brain moves in this direction. And so let me just describe how the weak coupling computation goes. So the idea is actually very simple to what Steve talked about last week. So the first step is to just represent determinants by fermion integrals like this. And the next step is to just integrate out n equals 4 super mils. And that is going to give you some effective action for mesons, which are bilinear of these fermions. And in the present case, because we are considering like a 3-point function of 2 determinants and 1 single trace, this meson is given by 2x2 matrices. And another nice feature is that if you write the effective action of the meson, then it comes with a factor of n in the large n limit. So in the large n limit, you can actually evaluate it at the saddle point. And there was a very nice paper today, and which basically showed that the saddles of this row integral in the chiral algebra sector is in 1-to-1 correspondence with the D-brain in BCOV theory. So in the context of twisted holography by Costello and Gaiotto. So if you're only talking about determinant operators, then this is the end of the story. But what we wanted to compute is to compute a 3-point function involving single trace operator. So let's take single trace operator to be of this form. Then if you repeat this procedure in the presence of single trace operator, then you find that the final answer is given by some matrix trace, which takes a similar structure as the original single trace operator. But here, instead of like n by n matrices, which we originally had, we actually have 2x2 matrices, where essentially these matrices are given by the saddle point value of this row. And so, and in order to proceed, we can also rewrite this trace into an overlap between matrix product state and O. So, and where the matrix product state is defined in this way. And you can clearly see that if you just take the overlap, then you pick up particular term in this matrix product state, and that is given by this trace. And here I just drew the usual description of the matrix product state. And one nice thing about this overlap between matrix product state and the operator, which is the eigenstate of the Hamiltonian, is that this was actually studied a lot in statistical mechanics in the context of quantum dynamics. And what they found is that if you this matrix product is this overlap is non-zero if and only if the set of momenta are parity symmetric. So they have to come in pairs. So this is basically some selection rule, and it implies that matrix product state is invariant under the infinitely many charges. This basically means that matrix product state is what's called integrable boundary state, introduced first by these people. And on top of that, they found that this overlap is given by some simple expression, the factorized part, times ratio of determinants, where determinant is basically defined by log derivative of the Betti equation. And I should also mention that n equals 4 super Mills also gives generalizations of these known formula, for example, to the SL2 spin chain or supergroup spin chain and so on. So that was the story for the weak coupling. And so how do we compute it at finite coupling? So in order to compute it at finite coupling, you need to use the string theory picture. So as I said, determinant operators creates DeBrain. And if you have a single trace operator on top of that, then that is described by a process in which DeBrain absorbs a closed string, which on the worksheet is nothing but this overlap between boundary state and the closed string state. So this is basically some generalization of what's called G function, introduced first by Affleck and Ludwig. And in order to determine this overlap at finite coupling, we first determine the reflection amplitudes against this boundary using like a consistency condition, which we call integrable bootstrap. So this is the reflection matrix. And the kind of constraint that we impose is like a symmetry constraint and boundary Yang-Baxter equation and boundary unitarity. So I'm not going to give you details, but what's most important is that this boundary Yang-Baxter equation, which basically is a statement that this boundary state corresponds to integrable boundary state. So this is an assumption. And in step 2, once we determine this reflection amplitude, we consider now cylinder partition function and take a limit where the length of the cylinder is very, very large. Then in this limit, we can expand the cylinder partition function into the closed string sector, and that is given by this expression. So this is a sum over closed string state, and there is an overlap term, and then there is a propagation term. And the same partition function can be viewed also from the open string theory side. And if you view it as from the open string theory side, it's nothing but the thermal partition function at inverse temperature equals L. And so this is given by some thermal partition function of open string. And in the limit when R is very large, you can replace the sum of open string states by a path integral of density of excitation. So this is a bit like a hydrodynamic-like representation in which you replace a state with some kind of density of particles. And in this expression, what is nice is that, so in this expression, so you have like some effective action, and this effective action is determined by the reflection amplitude that we determined like earlier in the previous slide. And what's most important here is that this effective action comes with a factor of R, and in the limit of large R, you can evaluate this saddle point, this path integral at the saddle points. And if you compare this expression against the expression coming from the closed string, you can clearly see that different saddles corresponds to different closed string states, and the saddle point equation is nothing but what's called TVA equation that I mentioned earlier. And if you carefully compare it, then you can easily see that basically one loop determinant gives you this factor that we wanted to compute, this overlap that we wanted to compute. So using this strategy, we can just compute it And the final answer is given by some kind of ratio of Fredholm determinants. This overlap is given by two factors. The first factor is some free factor, which depends on the details of reflection amplitudes. And the second factor is the Fredholm determinants, which also showed up in the talk by Clifford last week. But here it takes a little bit more complicated form because this like an integral kernel actually acts on a vectoral function rather than a single function because this S is a matrix. But the detail is probably not so important. And what's important is that it reproduces and generalizes the weak coupling answer. And furthermore, what's nice about this method is that a variety of quantities can, in principle, be studied by the same methods, including things like the instantons. And let me just highlight one intriguing observation. Which is like this. So if you consider, so in all these examples that I showed in the previous slide, there is one interesting common feature, which is the fact that if you do the computation at weak coupling, you get a matrix product state with bond dimension D, and that number D is exactly equal to the number of boundary bound states which appear at finite coupling computation. So this is just an observation, but it's very interesting because it basically tells us that a part of the Worldsheet degrees of freedom, which is the number of boundary bound state, can be seen already at weak coupling. Okay, yeah, actually, I might be a bit fast. But okay, let me just go to the lessons and future direction. So here, like today, I showed several recent developments about integrability, but I think one of the most important lessons that we can learn about all these integrability approaches is that the large Feynman diagrams is really the same as string worldsheeting ADS. Of course, I think people kind of knew it, but integrability has shown us that there is a precise sense in which this is true. And given this, I think it's kind of interesting to ask, for example, to ask whether we can do something similar in a different setup, for example, at finite temperature. And the second lesson is a little bit more technical. Basically, integrability tells us that 't-Hooft expansion in the large N limit has a finite radius of convergence. So this is also something known, already in the works by 't-Hooft. But because of integrability, we now know that what is the radius of convergence for many quantities. And the radius of convergence is pi squared. And in addition, integrability tells us that, or indicates or suggests that below this branch cut, there are actually infinitely many sheets. And so, and also there is a singularity at lambda equals minus pi squared. So given this presence of singularity, I think it's kind of interesting to ask whether we can take some double scaling limit near the singularity at minus pi squared. And by the way, I just wanted to mention that this kind of double scaling limit was previously speculated by Polakov that it might have some connection to DS. But I guess a more reliable but exotic version was discussed in this paper. So let me end by repeating this question. So there are two open questions with can we do the finite temperature analysis and can we see a horizon from the large N Feynman diagrams? And there is some interesting feature in the analytic property of the 't-Hooft coupling, and maybe it might be interesting to explore the double scaling limit. Okay, with that, let me just end my talk.
Thank you very much, Shota. Please, any questions? Just raise your hand.
There are people who raise hands.
Unmute Amit, you're muted.
Nathan, please.
So
Zero.
is it understood better now, the relation of integrability on the worldsheet and on the spin chain? I mean, has there been progress on understanding the relation?
Yeah, well, I don't think so. I think like there are developments about understanding on both sides. For example, on the worldsheet side, people succeeded in relating the integrability of the ADS5 times S5 to 4D Chern-Simons theory by Costello and others. And on the spin chain side, there are some works by Bizard in which he tried to kind of derive the integrability of the action, but I don't see any like a connection yet.
Okay, thanks.
Leopoldo?
Hi, thanks. Thanks for the talk. Can you elaborate a little bit more about the potential connections with horizon and black hole physics?
Yeah, well, I don't have much to say, but I guess at finite temperature, it's important to take into account the holonomy coming from S1. And that corresponds to some kind of like a winding mode on the worldsheet, or like some people call it vortex. And I guess like a condensation of the vortex is going to play an important role. And so on the pure string theory side, something similar was discussed like in this paper. But yeah, I think there are several more things that we can do on the Feynman diagram side.
Giovanni?
Hi, Shota. Thanks. My question is related to Leo's. So my understanding is that if you're looking at finite temperature correlators, one approach would be to look at the operators with dimensions of order n squared and look at their observables. But as far as I understand, this is not completely within the remit of integrability, or at least we don't know how to make contact directly. Can you say anything about prospects? Or even
so I'm not saying that like we can compute them using integrability, but integrability has told us that like there is a precise sense in which we can identify the Feynman diagrams with the worldsheet. So we should be a bit more optimistic and trying to see some features of like horizon or finite temperature physics from the Feynman diagram. So that was my point.
Maybe I can ask a slightly more technical question about finite temperature physics. Is it possible as a stopgap, instead of looking for a horizon, to see that at finite temperature correlators have poles and no cuts? That's from coupling. This is a prediction from ADS-CFT, because in weakly coupled theories, the analytic structure of thermal correlator has cuts from multi-part.
Right.
You only see quasi-normal poles.
Yeah, that's a good question, but I don't have anything to say about it.
Thanks.
Igor?
Thanks for a very nice review. The fact that the singularity is at minus pi squared, I guess, implies that one can go smoothly from 0 to infinity along the positive lambda, right? And that's related to the fact that you typically get alternating sign series, right? If you develop perturbative series. As far as I know, it's a rather special feature of the n=4 super Yang mills. Do you have any comments on how big a class of gauge theories have this property? Like, say, are some n=2 supersymmetric theories like this? What is known?
Well, yeah, I don't really know. Well, I guess like to make progress, I guess we can, for example, use the localization result, because this pi squared also showed up in Kongao's talk. So probably we can study some like integrated correlator or like a sphere partition function.
Emil?
But in QCD, it's unlikely to work like this in non-supersymmetric.
Yeah, I don't have much comments.
Okay, thank you.
Martinek, please.
Yeah, very interesting. So in the second part of your talk, you discussed perturbations around giant gravitons.
Yes.
So what are the prospects of generalizing that to more general LLM type geometries?
Right. So at weak coupling, one can use the same technology, like introducing fermions. Well, you need to like introduce several fermions and then write some effective action. But at strong coupling, or sorry, at finite coupling or from the integrability side, right now there is no strong evidence that we can study it using integrability. Although, like I should mention that there are interesting works by Domelokova and others in which they kind of suggested that there might be some integrable subsectors, but even that question is not settled yet.
Okay, thank you.
Kazakov? Volodya?
Sorry, I'm not visible. Thanks, Shota, for a nice review. It's a great contribution to our tomorrow's discussion with Gregory. My question is, could you imagine some formula generalizing this integral over 3Q functions for triple correlator for your quantities, like 2 determinants, one operator? Could you imagine how to combine it from Q
Okay,
function?
yeah. That's a good question. And actually, like at weak coupling on the spin chain side, we already have the expression. So like this overlap can be expressed as a multiple integral of Q function. For example, there are expressions for the SU2 spin chain.
What do you do with what does correspond to determinant then? Some exponentiation of Q function or?
Oh, no. Well, you just, okay. So it's actually interesting. So I pointed out some similarity with the matrix integral, and which like so there is some like a fundamental like factor which is given by sinh and x, right? And you basically like need to replace that factor by something like a sinh of xj square minus xk square times xj square minus xk square, which is a bit like going to like a from GUE to GOE. And okay, it's just a change of measure.
Thank you.
Any more questions? Note that we will have tomorrow a session about integrability. So if you have more questions until then, you can ask it tomorrow. Frank, maybe want to share your slides? Let's thank Shota again for the very nice overview.
I mean, let's just wait a few minutes just because some people may tune on just at 2:30. So.